Now we need to talk about numerical stability condition. First of all, I need to introduce two terms, explicit and implicit. In solving differential equation, and here we are multivariable, so it is multivariate partial differential equation. The numerical schemes, which we have finite volume schemes or finite difference scheme, can be classified into explicit scheme or implicit scheme. So here are the figures showing the ideas. So in the y-axis, you see the arrow with t, which means time, evolution of time. When you are doing the time integration, actually there are two ways to do it. The first way is to express the relation from at a location in the future to be dependent on different location of the present. This is one way of solving the partial differential equation. And the other way is the reverse. In the relationship, you express the relation to have several locations in the future. But for the present time, you only put one location here. And then the relationship is between several locations in the future to one point at the present. And if you solve it mathematically, this is more difficult to solve because you need to solve a coupled set of equations. Each will have 3 locations in this example. But for the explicit scheme, it looks like easier to solve because for each equation, you just need to calculate the variables at one location given the present variables at 3 locations. So for atmospheric model, handling the horizontal direction, we use explicit scheme. We use this kind of relationship in the equations, in the implementations that solve the equation. However, there is a drawback. There is advantage and drawback. The advantage is the program becomes easily parallelizable because when you write a program to implement the calculation, each calculation is for one location of the future points you want to calculate. So you may put one area to be handled by one CPU and another area to be handled by another CPU. Of course, there is some more tedious things that across the 2 areas, there is some dependency, and these are actually handled by the software engineer that use some, we say, MPI, message passing communication to send the data of the present atmospheric state to the needed recipient, the other CPU, and then to continue the calculations. So this kind of parallel computing needs a pretty good network for the computation to be fast because it depends on the neighbor's data, which across the partition, you need communication. And this is the virtue that this explicit scheme can be easily parallelized. For implicit scheme, the coupling is so troublesome that it is difficult to parallelize. So we need to discretize the whole atmosphere into a large number of cells, as you have already tried, and you have 200,000 horizontal cells. So you need parallel computing. So you need to use a implicit scheme. But you also suffer from the drawback of explicit scheme because it needs a numerical stability condition to be satisfied for you to go on the calculation, or otherwise, we will say that the simulation will numerically blow up. That means you will see not a number or unreasonably large number appear as the time integration go on. And if that happens, we say that the simulation is numerically unstable, and that will result in nothing. Basically, you will get an error in your real simulation job. So we have to understand what numerical stability condition is. And here is the Wikipedia page. The name of such a numerical stability condition is called CFL condition. CFL are the beginning letters of three mathematicians, and the first mathematician is called Coulomb. So sometimes we call it the Coulomb condition. So the principle behind the condition is that, with this sentence, if a wave is moving across a discretized spatial grid, and we want to compute its amplitude at discrete time steps of equal duration, then the duration must be less than the time for the wave to travel to adjacent grid points. So this is the statement. I hope this statement already gives you some idea, but maybe you need some example for you to understand it intuitively. Here is one example also from Stu's book. Consider this situation. The grid spacing delta x has a 3 kilometer grid spacing, and the wind speed is 10 meters per second. So mathematically, staying it out, the CFL condition is this constraint on delta t. The time step must be smaller than or equal to the grid spacing divided by the wind speed. So here are three examples. If you carry out a simulation with delta t 100 seconds, and if you do some calculation, it is only 3.33 relative to the term on the right-hand side. So it is smaller. So the initial state is the black curve, is represented a black curve. There is a wave in the model, and it is propagating. In the next time step, it is the red line. After you calculate the next time step, you see that it seems that there is no problem. The wave propagate, and you carry out more time steps, you will see that it is nice. It is just simulating the wave is moving to the right. Okay, this is numerically stable. And you are spending the computation cost to calculate, to do the calculation steps once every 100 seconds in the simulated time. How about use a longer time step, say 250 seconds, and you carry out the simulation. The next time step, which is 250 seconds later, the wave propagates to a longer distance. But you will see that it seems that the simulated result is also normal in the way that the wave just propagate. And now after this many number of steps, the duration is longer. So this dotted line shows the case that the wave propagated a longer horizontal distance. So in this case, you are using a longer time step, but it is still stable. But if you want to save more computational cost by using an even longer time step, what will happen? The simulation result will be the first time step, the wave seems to have a bigger amplitude, which if you use a smaller time step to simulate it, it is different. And then the amplitude of the simulated wave is getting bigger and bigger and bigger. And actually, at a later time, it will exponentially increase. And then you will have very large number appearing as temperature or wind speed or whatever in your simulated atmosphere. And then finally, the computer program will result in not a number represented in the data field in the data. And you often encounter that in Python programming, okay? So in this case, we say that the simulation is already numerically unstable because you used a large time step. And in the best practice, which is written in the documentation of WRF, WRF, and also its older generation MM5. And as the developer further develop MPAS with the unstructured grid, many principles that is applicable to MM5 and WRF also applies to the MPAS model, although it uses an unstructured mesh. So from previous experience, the rule is that the time step used needs to be proportional to the grid spacing. Underneath, there is some assumption of the highest wind speed that will be present in the simulated atmosphere or something like that. And this is the justification behind the best practice. And from experience, it is safe if we stick to the best practice, the engineering way of using a software product. Then we continue to stick to this practice. So this practice suggests a factor 6 seconds per kilometer or smaller.